MS 17182 for the PHY 637 term paper presentation. My topic of presentation is globular clusters, which in my presentation I will be reviewing these two papers which I got for review. So this is the overview of my talk. First, I will talk generally about the globular clusters and their properties. After that, I will talk about the age determination methods for the globular clusters, which were discussed in the first paper. And then after that, I will talk about the age metallicity relations of the globular clusters, which were studied, and some important correlations that were found in them. And then I will talk about the relation of those correlations with the Milky Way evolutionary history. So moving on. So basically, globular clusters are the dense star clusters with spherically symmetric shape because they are tightly held by the gravity. A typical globular clusters looks like this. We can see that the density increases as we go towards the center. This is NGC 7006. The globular clusters typically contain stars around 1,000 to million stars, and their size varies. Size is around 10 kiloparsecs. The first global cluster, now named M22, was found in 1665 by Abraham Isle, and after that, in the 18th century, many globular clusters, about 60 to 70 globular clusters, were found around the Milky Way galaxy. The globular clusters was also used to get the idea of scale and the relative position of Sun in our galaxy. Basically, to get to know that Sun was not at the center of our galaxy. Um, So most of these globular clusters are found in the Milky Way galaxy halo or in the disk, and some are also found in the disk of the galaxy. The halo is this region around the galaxy, and the disk is the major populated region. The Milky Way has around 150 globular clusters, which are found till now. So, more on globular clusters. Globular clusters are referred to as stellar clocks because of the following reasons. All stars in globular clusters were formed are believed to formed at around the same time. The globular clusters have homogeneous metallic appearances, and no new star formation usually is taking place in the globular clusters. Because of this, they can be used as stellar clocks um, to uh, to tell us about means the exact their ages of importance. So they are found to be extremely or their ages are found to be extremely old, and their ages are found to be comparable to the age of universe, and that they are one of the factors that are used to put the lower limit on the age of the universe. Their ages varies from 4 to 13 billion years. We can see that their ages are comparable to the present age of the universe, which is 13.8 billion years. Uh, so the ages of globular clusters are interesting because first, as we have seen, they are used to put the lower limit on the age of. They are one of the factors that put the lower limit on the age of the universe. And secondly, if we know about the exact age of the globular clusters, we can use them to infer about the formation of globular clusters and the evolution. And it can be important. It can play an important role in telling us about the evolution of the universe and the formation of galaxies in which they are found. So a typical way in which we can infer a age of a star cluster is by looking at their main sequence turn-off point. Like if the turn-off point is lower, the star cluster is it means that the most of the stars in the star cluster have gone off the main sequence, and it means that star cluster is older than the star clusters in which stars are still going off the main just now going off the main sequence. Like the star clusters above are younger, and these star clusters are older. So in the globular clusters, the methods used for age determination are which were discussed in the paper were these two. First is the main sequence turnoff, fitting this main sequence turnoff with an isochrone, and second is this relative aging method, which I will discuss in the further slides. So main sequence turnoff fitting method is basically trying to fit the globular cluster CMD color magnitude diagram with an isochrone. Isochrone is a theoretical evolution curve of a star cluster, which takes the initial mass function of the globular cluster and the metallicity as an input, and then we evolve it using a stellar evolution code, and then we try to match it with the experimental CMD diagram to get the estimate of the age of the globular cluster. As we can see in this figure, there are means the scientists are trying to fit the globular cluster with the different isochrones. The major limitation of this method is that if the distance to a globular cluster is not known precisely, so we can see that there the color of there is a degeneracy between the distance and the age. It means that this turn-off point depends both on the age of a globular cluster as well as the experimental turn-off point, as well as the distance to the globular cluster. So if we don't know the distance to the globular cluster, so it leaves our measurement ambiguous, and there is so this method demands the distance to the globular cluster to be known. And we can also see that the turn off point is also not quite easy to fit. Means uh, there the turn off point is wide, and there can be this also leads to error in the globular cluster, the globular cluster age. The error corresponding to these limitations are amount to about 3 billion years, can amount to as large as 3 billion years. The second method, which I will now discuss, is this relative aging method. And in this relative aging method, also we first fit the globular cluster main sequence part turn off point with an isochrone, and after that we also fit the horizontal branch of a globular cluster with also a theoretical zero age horizontal branch curve, which is also obtained from the evolution course. And then because then the age of a globular cluster is measured as the distance between the horizontal branch and the turn off point, measured at the same at the color of the turn off. So as we can see, the turn off point will eventually move down and move downwards, and it means that the larger the difference between the horizontal branch and the turn off point, more will be the age of the globular cluster. And in this method, we have removed the age distance degeneracy that was a problem in this method. But there is still a problem of turn off fitting. And yeah, and the another advantage of this method, which authors have mentioned, is that the uncertainty from the metallicities means as the theoretical isochrones take input as the metallicities. So uncertainties arising from the uncertainties in age arising from metallicities are minimized in this method, as both the horizontal branch and turn off point shift in the similar way due to changes in metallicity. So these are the two methods. The authors have used this method. The authors have used means a defined version of this method in the paper to determine the ages of the globular clusters found in the Milky Way galaxy. They have used this method to find the ages of about 55 to 70 globular clusters. And after determining the ages, they have used the metallicity. They have used the metallicity data from the metallicity from the spectroscopic data to plot the age metallicity relations of the globular clusters, which were plotted like this. Like these are the globular clusters, different globular clusters found around the Milky Way, and the x-axis is metallicity and y-axis is the age of the globular cluster. And the authors also tried they segregated the globular clusters by how much time they spent in the halo, and based on the fraction of time they spent in the Milky Way halo and the disk of the Milky Way as a halo globular clusters and disk globular clusters. And in this plot they have color coded. We have color coded these. The pink dots show the disk globular clusters, and the black dots are the halo globular clusters. We can at the first sight infer that there is a segregation of these two types of globular clusters on the age metallicity plot. And the halo globular clusters are clearly seen to be a metal poorer than the disk globular clusters. So yeah, disk globular clusters. And so then the authors try to extract more information from the AMR plots. The first thing that this is also showing the same. This plot also shows also confirms that the pink solid lines are the stars of the Milky Way, and this is the kinematic velocities and distance, the galactic distance. And we can see that the halo globular clusters are spread in the large area around in the Milky Way halo, whereas the disk globular clusters are found consistent with the are found in the area consistent with the stars of the disk. The interesting point here can be that the velocities of the halo globular clusters are found to be of the opposite sign than the disk globular clusters. So yeah, to extract the more information from the AMR plots, the authors try to fit the AMRs of the globular cluster, overlap the AMR of the globular cluster with this solid line shows the AMR of the Milky Way disk stars, and we can see that there is a overlap. There is a clear strong overlap um, between the disk globular metal rich branch of the globular clusters and the Milky Way disk stars. And this strongly shows us that the disk globular clusters are most likely to be found in situ in the Milky Way disk, and whereas their dotted lines are the AMR relations of the dwarf galaxy, dwarf galaxies, and the large Magellanic and small Magellanic cloud, and these are shown to be overlapping with the metal poorer branch of the AMR globular cluster AMR. And the authors have provided strong arguments for this overlap. by studying the galactic mass metallicity relations, which I have talked about in my term paper. And from here, they conclude that the halo globular cluster might have, they guess that halo globular clusters might have come from the dwarf galaxies, whereas we can see that there is a strong overlap between the disk globular clusters, which are most likely to be found in situ in the Milky Way disk. But to confirm this correlation, or I guess about the halo globular clusters, we the some particular some definite amount consistent with the number of globular clusters found in a number of globular clusters in the MR region uh, have to come from the dwarf galaxies, and they have to be consistent with the observations. And to further confirm this, the authors try to do the simulations of the accretion of the Milky Way halo and try to see whether there is a consistency between the number of globular clusters which are accumulated as the Milky Way evolves and accretes the dwarf galaxy surrounding dwarf galaxies with the stellar mass of the halo, Milky Way halo. They simulated the Milky Way halo accreting the subhalos and looked at the number of subhalos accreted as a function of cumulative mass of the Milky Way halo. The subhalos tend to contain the small dwarf galaxies which are accreted as the Milky Way walls, and each dwarf galaxy is found to assumed to contribute some particular number of globular clusters, which is called the globular cluster frequency. And from here, they were also able to plot the number of globular clusters accreted in the halo as a function of the mass of the dwarf galaxies. And the simulations were found to be consistent, found to be positive to conclude that the Milky Way halo globular clusters are likely to have formed are likely to have come from the dwarf galaxies. And the most of the globular clusters accreted from dwarf galaxies, which have the mass of the order dwarf galaxies, which have the mass of the order of 10 to the 7 to 9 solar masses. So this is I have talked more about it in my presentation in my term paper, and I have described these plots, so you can look up there. So with this, as the time is about to